Well, hi, everybody. I'd love to introduce Priya Donti from MIT, and she's been working on decarbonizing the world using OR and optimization methods, focusing on decarbonizing power grids. Welcome.
Yeah, thanks so much for having me. And yeah, I'm excited to be here. Yeah, so today I want to focus my talk on power grids. So power grids are a topic of really key societal importance for a couple of reasons. One, they're actually very central to our strategies to reduce greenhouse gas emissions and address climate change. So currently, a quarter of global greenhouse gas emissions kind of come from energy supply systems. And power grids are also the backbone for strategies to sort of decarbonize and electrify sectors like buildings and transportation, where a lot of strategies for decarbonization basically rely on moving away from fossil fuels to sort of electrifying those sectors. So power grids are obviously very important from these perspectives. They also provide very critical services for our lives. We kind of rely in many of our day-to-day kind of lives basically on the ability to kind of rely on the fact that the grid is actually, there, that we can turn on lights, that we can power our hospital equipment, all of that kind of thing. And so it's really critical that power grids are operated in a way that is sort of robust, such that if something goes wrong, they're able to kind of stay operating, degrade gracefully, resilient in the sense that if the grid goes out due to extreme weather, for example, that the grid is able to repair very quickly and bounce back, and that the power provided is reliable and high quality, that we can actually, make sure it's not going to degrade our equipment or electronics or anything like this. But then because we want to do all these things, because we want to reduce greenhouse gas emissions, we want to provide kind of critical robustness services, we're starting to increasingly see a power grid where we're trying to incorporate kind of more devices, right? Like more electric vehicles, more electric heating, where we're trying to decarbonize the grid by introducing more solar and wind and other kind of time varying sources of power. And where we're also introducing more batteries, more kind of flexibility on the grid to shift when certain consumers are using power and so forth. And so this basically is just requiring the power grid to be operated and planned at greater speed, greater scale, greater physical fidelity. And our existing optimization and control methods are struggling to kind of meet that scale, to meet that demand. So in terms of what I mean by operating a grid, so I want to give an example problem for what it would mean to actually operate a power grid. So a kind of a idealized operation of the power grid can be described through this problem called AC optimal power flow. And what this problem does is it tries to set the power and the voltages at all power generators that we can control on the power grid in a way that minimizes the power costs, meets the demand on the grid, and satisfies the various grid and operational constraints that we have on equipment. So that problem might look something like this, where we have some optimization problem. We're sort of setting power generation and voltages. Since this is an AC power system, power has a real and imaginary part. So that's what that P and Q are, and voltages also have a magnitude and an angle. And the goal is to minimize the cost of power generation, subject to various constraints that basically say, I have limits on kind of how much power each generator can produce. I have limits on what my voltage value can be at different points on the system. And I have limits on how much power can flow on any given line in the system. And then I also have to satisfy what is called a power flow constraint, a nodal power flow constraint, which basically says that if you think of your power grid as like a graph, that the flow of power into every node has to exactly equal the amount of power flowing out of every node at every moment. And because of the way these variables are formulated, this ends up being kind of a quadratic equality constraint, like a non-convex constraint. And as a result, this problem is actually non-convex, NP-hard, computationally challenging to solve.
Good. This is a quadratic system, not a quadratic number of relationships, or both.
So it's that the form of the power flow equations is quadratic, but it's not. Yeah, it's not that there's a quadratic number of relationships. Okay. So it's more about the form of the problem rather than the size necessarily that I'm saying this. Yeah, exactly. And then for those who are curious, like actually the prices for power on different parts of the power grid, the wholesale prices are also kind of based on this problem. They end up being the dual variables on this power flow constraint. And so, yeah, so this problem ends up being non-convex, NP hard, and we do also have to solve it at fairly large scale, kind of on real world systems. We're talking systems that have like 1,000 to 14,000 variables at minimum. And yet we need to solve these problems in seconds in order to kind of allow us to operate power grids day to day. And so one approach that's been proposed to address this is something called amortized optimization. And the basic idea is that if you kind of abstract away the problem that I showed on the previous slide, this optimal power flow problem, you can think of it as basically an optimization problem that has an objective and constraints. The constraints vary from time to time based on input. So for example, my power demand varies from one moment to the next. That would be captured in this X here. As you can think of my power demand as kind of parameterizing my objective and constraints. And then given like a particular instantiation of power demand, X, then I would basically want to understand what the solution is. Like, how do I actually schedule my grid? That would be Y. And you can kind of think of different instances of this optimization problem as kind of they have a varying parameter like demand between different instances, and you're trying to learn some mapping between the input, the demand X, and the output, your decision Y. And so the question is, can we actually use machine learning to learn this approximation, to approximate this mapping in a way that is very fast to evaluate when you actually need your answer, so you can get this kind of fast real-time power grid operation? And so what is hard about this, right? Like, why can we just not do this today? And I think it comes down to the fact that to solve this problem, to solve many other problems on power grids, there are many kind of requirements that these algorithms need to satisfy to actually be usable on real world power systems. So one of them is that they need to be safe, that the kind of methods, the outputs of these methods fundamentally need to satisfy hardware and equipment constraints on the power grid. Otherwise, you get a large scale blackout, which you definitely don't want. And naive machine learning methods don't necessarily satisfy constraints by default. The other thing is you need them to be robust. So even if you get kind of unexpected or extreme inputs, like a demand profile that isn't what you expected, or you have some kind of outage of a generator due to some maintenance issue, you want the model to still perform reasonably under these scenarios and kind of degrade gracefully if it's going to degrade. You also need models that generalize across different settings. For example, the topology of the power grid, the actual connectivity structure of the power grid, is actually changed by power grid operators every so often, using kind of switching equipment on the power grid. And so if your model is assuming that you only have one fixed topology, then it's not going to work well in situations where you now actually have a different power grid topology. You need to generalize over that. And kind of aspirationally, there's a desire to also say, well, like some of the power flow functions or the power system functions that we're performing on different grids are actually the same. Can we even learn one model that is usable across multiple different power grids? So generalizability becomes important. In addition, machine learning models in this setting are multi-agent. So when you have kind of a model that's scheduling power in one part of the grid, there's another model or workflow being used somewhere else to schedule power somewhere else on the other grid, on a different grid. And so all of these kind of controllers and optimizers together need to actually be able to work together to come up with good outcomes for the grid. And these are not just all automated controllers. Actually, a lot of functions on the power grid today are done by humans. So when today power is dispatched on the power grid, sometimes a grid operator, a human, is picking up the phone and calling the owner or operator of that power generator to say, hey, can you change the power generation a little bit? So basically, kind of models also need to work kind of in the loop with humans in these systems. And so today in my talk, I'm obviously not going to be able to get through all of these areas. I just want to pose these as kind of important requirements for machine learning in power grids today. But I want to focus primarily on this notion of safety. So how do we kind of ensure that machine learning model outputs are actually satisfying constraints that we care about? And so today in the talk, I want to talk about maybe kind of 3 different ways that we've thought about doing this in the context of machine learning for power systems. each of which comes with kind of different trade-offs, right? Kind of some have better guarantees, some have better computational performance, and you're also often trading off between these things. So I want to talk about a few different methods and also talk about these trade-offs. So the first method I want to present is something called optimization in the loop machine learning. So the basic idea is that we kind of have machine learning models, and naive machine learning models, their outputs are not going to sort of satisfy a constraint. Their output is not necessarily going to kind of just by default like lie on this power flow satisfying manifold that we care about. And so what we do is actually develop custom neural network layers that actually reflect the actual equations that are used on power grids and figure out how to embed those into neural networks to sort of force the neural network's output to be safe. So what this looks like is kind of imagine you have a neural network. This neural network, right, you can think of it as a bunch of functions composed together, a bunch of layers composed together, where each layer needs to be able to map from an input to an output. And in order to train this neural network via backpropagation and gradient descent, you also need to be able to take gradients of sort of loss functions with respect to each of the parameters and inputs in this network. So basically take the gradient through each layer. And while there are sort of standard types of functions that we often think of in these neural network contexts, right? Like, ReLU, tanh, now attention layers and things like that. In principle, kind of any function that we can kind of make satisfy these two requirements of having the ability to map from an input to an output and having the ability to take a gradient of the output with respect to the input, any layer that we can make meet those requirements can in principle be stuck into a neural network as a layer that we can use for various things. So traditionally, the kinds of neural network layers that we think of, like attention layers, like ReLU-based layers, like tanh-based layers, and so forth, are what we would call explicit layers. And so explicit layers are layers based on explicit functions, by which I mean, if you have some kind of input x and some set of parameters theta, and you want to get some output z from your neural network layer, for most neural network layers that we think about, we can basically just plug x and theta into one side of the equation, and then z spits out on the other side of the equation. Kind of the idea of how you get from your outputs to your outputs from your inputs, it's pretty easy. You just stick them into an equation. So for example, kind of our standard, like you have an input and it goes through like a linear transformation and then a sigmoid and you get your output. This would be an explicit function, explicit layer. And then when we think about taking derivatives, when we say what is the derivative of the output with respect to the input, we just sort of take the derivative of the right side of the equation. Like it's a very natural thing to do to take derivatives with respect to an explicit equation. Now, what happens if we actually have an equation where our inputs and outputs are not separable? So if you think about like differential equations or power flow equations or optimization problems, these aren't problems where you can just rearrange the equation to put your inputs on one side, your output on the other side, and then kind of stick your inputs on the other side and solve for the output. These are situations where you often need to use like an iterative solver, right? Like a differential equation solver or kind of Newton-Raphson or like a nonlinear solver of some sort in order to get your output. So implicit layers try to capture functions that have this characteristic, where you're needing to use some kind of iterative solver in order to solve them. And this would be things like our power flow equations, or if you're computing like a project this point onto another set, like that would be this kind of thing.
So just to clarify, because this is does not smell like the same as physics implicit explicit. This sounds like more of a time series notion of next time step based on last time step.
No, it's sort of the same notion of if it's like in physics. It's like kind of for one solve involves doing like an iterative process to solve like a numerical equation. So
it is like I have like next time step and last time step together and then figured out the details.
Exactly. It's exactly like that. And sort of like in kind of an explicit formulation in physics, right? It's like previous time step goes on the right side of the equation, and then next time step spits out on the left side. In an implicit formulation, like both of them are in a way such that you have to kind of like solve some iterative equation to figure out what the next time step is.
Yeah, in order to get
So
the
it's
next
like
time
that.
step like this, you have what else has to happen? Yeah. And
Yeah,
so that's explained
exactly.
here. Yeah.
Yep. And so in these situations, then the question becomes, okay, now I've told you how to sort of solve for your output based on your input. Let's like use your iterative solver. But now how do I take gradients through this to enable backpropagation and gradient descent? It turns out you can use something called the implicit function theorem, which basically says that at the solution of your kind of like, if you have a solution that satisfies your implicit equation, then at that solution, you can basically view your outputs as a function of your inputs, and you can take gradients in the way that like you sort of naturally would if you were doing them algebraically. So essentially the idea is that for these implicit iterative solvers, in the forward pass, you solve it and you make sure you actually solve it to like some level of precision. And in the backward pass, we can then basically take derivatives at that solution of the output with respect to the input in an analytical form. So let me give
Actually,
one
that's one more
example.
question.
Yep.
Don't you have enormous gradients when you do it this way? And what do you do about that?
So
It
you
seems like a
don't.
very long procedure.
No, and so this is so the whole kind of there are two ways you could think about taking gradients through like an iterative procedure.
Mhm.
One of them is like you think of it in the forward pass as this like unrolled procedure, and then you take gradients through each unrolling. That can indeed lead to kind of gradient blow up issues. What the implicit function theorem approach does is actually it avoids that entirely. It basically says I have an equation and I have a solution to it, and I don't actually care how you got to that solution. You could have used some
Mhm.
iterative solver, you could have just guessed and gotten the right solution. But basically, I can give you kind of given that equation, like an analytical solution, an analytical expression at that solution point for the gradient of the output with respect to the input. So you don't end up taking derivatives through the entire unrolled iterations. You just take like you have like one equation that you use to solve for the
That's really
gradient.
convenient. Thank you.
Yeah. And so actually I'll instantiate this to give one example to try to make this more concrete. So imagine that we're our neural network layer that we're solving is solving a quadratic program. So in like our neural network layer will take in as input the parameters of this quadratic program. So like the big Q, the little q, A, B, G, H. And then the output of the layer is the solution to this optimization problem. So it's actually like I've solved the optimization problem. That's what my neural network layer did. It gives me Z. So then I have a solution, Z star, and I want to understand how do I get the gradient of that solution, Z star, with respect to all of the inputs, the Qs, the A, B, G, H. It turns out that for optimization problems, we have, right, this set of equations called the KKT optimality conditions that especially for convex problems are necessary and sufficient to describe all solutions of the problem. So we essentially have like a set of equations that the solution satisfies at optimality. What we then do is we then actually take the derivative through this set of equations in order to understand kind of what is the gradient of our output with respect to our input. And so that ends up looking something like this, where all we've done is basically like this D notation is basically like our generalized notation for the derivative of Z with respect to any arbitrary input parameter. So this equation could be written for big Q, it could be written for little q, but this notation here basically says the gradient of our Z with respect to one of our parameters. And we basically like just take derivatives of this these KKT conditions with respect to any of our arbitrary parameters. You kind of do all your standard rules, right? You have your product rule and stuff like that. You rearrange the equations and you end up getting something that looks like this, where this middle term is our desired gradient. So we're trying to get the gradient of our output Z with respect to like Q. So that would be captured in there. the left side ends up, what it's multiplying ends up being the generalized Jacobian of our KKT conditions. And the right side ends up being the gradients of our problem parameters. And so if this exact detail, like I didn't show the like full out derivation, right? So if the exact details are sort of not entirely clear, don't worry too much about that. But the basic thing I'm trying to capture here is you have some layer that's kind of capturing some iterative, some procedure that you would solve with an iterative solver, like an optimization problem where your layer is taking in optimization problem parameters and is outputting the solution to the optimization problem. I then am able to express some set of equations that is satisfied at that solution. And then I can take gradients analytically at that solution without having worried how I got my solution. Like nothing in these equations is telling me like, what was the process that I used to solve the optimization problem? What were the iterates, etc. I can just take a snapshot of what the solution is and take gradients at that point.
So it's actually interesting that you don't need that. Well, I guess the original optimization process had to have been differentiable to work, but you just ignore all that stuff. You just go to the match.
You actually don't even need the original optimization process to be differentiable. In some sense, you can think of it as this black box where it's like, I have a process, it was solved, and I know what the equations were that were solved. And just based on the fact that I know what the equations were and I know what the solution to those equations is, I can get the derivatives without having to worry about any details of how it was solved. It could have been solved in a non-differentiable way as well.
Actually, that makes sense. It is literally because you have the equations, it could be just magic. Somebody popped you a solution. It's the equations that make it happen, not the solver process. Got it.
Exactly. And so for those who have like worked with or heard of like neural ODEs or have worked with differentiable quadratic programming layers or have worked with deep equilibrium layers, that's how all of these work, basically. It's sort of like you kind of have some iterative process, you solve it, you don't actually care in some sense how you solved it, but you're able to use the specification of the equations and the solutions to figure out the gradient.
Got it.
Yeah, awesome. All right, so how do we kind of like bringing this back to power systems, how do we use this kind of thinking for power grids? So one problem that we try to solve is the problem I motivated at the beginning, which is solving this problem of AC optimal power flow. As a reminder, the problem where we're trying to schedule our power generation to minimize costs, subject to the AC power flow constraints and various device limits. And we want to learn kind of a solver for this set of equations using machine learning that is fast to evaluate at runtime, but that also definitely satisfies the constraints. So one way we propose to do this is we have a neural network. That neural network is going to take in the same inputs as AC optimal power flow. In this case, we're going to say the power demand on the power grid varies between instances of this problem. So that's going to be our input. And then our neural network model is going to output sort of a either partial or full solution. And we're going to then make sure that that solution actually satisfies the constraints. So we're going to put that through some constraint enforcement layer or set of layers that make sure that the output on the other side is constraint satisfying. And then we're going to basically kind of look at that output and ask, is it good? We're actually going to do this in a self-supervised manner. So we're going to basically say, my ACOPF solution is good. Is it if it has a low kind of objective value, it like minimizes costs. If there aren't any infeasibilities, so if we satisfy all the constraints, and also we add a term to help with training that our constraint enforcement layer didn't have to do too much work, that the kind of input to the constraint enforcement layer and then the output of it, they weren't so far apart. And we're then going to propose to train this pipeline end to end in order to learn like a good solution to the AC optimal power flow equations. So in different works, we propose different ways that the just like
on the stream, yeah. So there, are you guaranteed going to find a solution to these equations?
Say that again. Sorry.
Are you guaranteed you will actually find a solution to these equations?
So yes and no. So basically, there's two things that can kind of go wrong, and like maybe let me hold that question till I talk about the details of the constraint enforcement layers, and then I'll come back to that. But yeah, that's a great question. Yeah. So there are kind of different things we proposed in different works for how the constraint enforcement layers can look. In one work, what we propose is that the neural network basically gives a kind of partial output to the optimal power flow problem. And then we solve the power flow equations to get the rest of the outputs. So basically, the neural network is outputting some kind of fraction of the outputs, like some of the power generation at the power generators, for example, and the voltages at the power generators. But the AC power flow solver is being used to solve for the voltages everywhere else on the grid. So we basically kind of, in an optimization problem, because we have like only actually a certain number of degrees of freedom, because we know that our equality constraints have to be satisfied, we only predict a number of variables equal to the number of degrees of freedom, and then we actually solve the power flow equations to get the rest of the variables. So this AC power flow solver is an example of an implicit layer that we would use. We then get an estimate of the full state of the power grid, but then it's not necessarily guaranteed yet that those variables satisfy our inequality constraints, like the device limits about like how much power a particular generator can produce. So we create sort of another module based on implicit layers that actually corrects our device limits. What this module basically does is it kind of walks in the direction of satisfying the inequality constraints while never leaving the AC power flow equations, while never leaving the equality constraints. So we do this basically like two-step implicit layer-based procedure, and then the output is something that like should basically satisfy the constraints. It will definitely satisfy the AC power flow constraints, and it will empirically satisfy, in this case, the device limit constraints. The other approach we look at is an approach where the neural network actually outputs a proposal for the full set of variables. So like all of the powers, all of the voltages on the grid. But then we use that to warm start a constraint minimization optimization problem. So we have this sort of feasibility seeking optimization problem where we're basically saying, use this as a warm start and iterate the solution to make it minimize its violations of equality and inequality constraints until you get to the corrected full state. So these are just like kind of two different approaches. And the idea is that we are doing something expensive in both of these cases. In the first case, we're solving an AC power flow solver. In the second case, we're solving an unconstrained optimization problem in the context of our neural network pipeline. But doing that kind of gives us a nice trade-off between it's less expensive to do that than to solve the full original optimization problem online. For example, here we're reducing what we're doing during inference to like a unconstrained optimization problem instead of a constrained optimization problem. So it's cheaper to do online than solving the original problem, but it still allows you to kind of satisfy constraints during this. So to Greg's question about kind of like, are constraints kind of guaranteed to be satisfied here? So first of all, like if the problem, like the original problem actually, like you've given it an infeasible instance, like there is no actual solution that satisfies constraints, then in that case, of course, no pipeline can give you a constraint satisfying solution. This first method will actually break in that situation, in the sense that because of the specific way the implicit differentiation is set up, if you can't find a solution, then you also like you're not able to get your derivatives. This second pipeline is able to deal with that because the way the problem is set up is that it should minimize the violations of constraints. And so if there's a kind of a solution, if there exists a solution with zero constraint violations, this problem should find it. But if there doesn't exist a solution with zero constraint violations, then this should just settle to some local minimum that has some constraint violations, but it'll still kind of solve. The other thing that can happen is that if your neural network output is just very bad, it's possible that your iterative solver just won't converge, even though there in principle exists a solution, and then that breaks the pipeline as well. So often in practice, you'll use some tricks to condition the input to the iterative solver to make sure that that doesn't happen. So for example, for this version of the algorithm, you can you know ahead of time that there are some minimum and maximum power generation limits for your power generators. So you sort of make sure using sigmoids that your dispatch falls within this minimum and maximum of the power generation. And then because power grids are designed robustly, if you have like a reasonable power generation schedule, then the AC power flow should converge. So you basically play some tricks to make sure that the inputs to your iterative solver are not kind of so wild that the iterative solver won't converge.
So question, a lot of this seems to be skating on the edges of NP hardness, right? You have optimality things where you're okay being not fully optimal, but also it seems like the way you design a power grid is that it doesn't go too wild, and a lot of the NP complete things just still happen by design. So to what extent, I guess what extent are you being successful in skating on the good side of NP hardness, and what are you losing by doing so?
Yeah. So the thing that you are sort of able to do here, what we're basically trying to say is that like coming up with an optimal solution to a problem is much harder than coming up with a feasible solution to a problem. And so if we can somehow during inference get a good solution for the cost of basically doing one feasibility correction, that's better than having to solve the full optimality plus feasibility problem online.
Mm-hmm.
And so then during neural network training, we're trying to kind of build in, during training and inference, we build in the feasibility part, but we let training kind of take care of trying to come up with a good solution. So it's taking care of the optimality part. And here the neural network has no guarantees, right? Even though we can guarantee that the output is feasible because of the way we build the neural network, we can't guarantee that the output is necessarily optimal because that's what we're using data-driven learning for. And so empirically, we see that we're able to learn good cost solutions, but what you lose is the guarantee. You lose the guarantee on the optimality side. And here, the reason we're okay doing that is because in power grids, kind of if you're slightly cost suboptimal, that's okay as long as you're definitely feasible. So that's the trade-off that we actually want on power grids.
And in what way are we designing power grids to make this more likely? Because I'm noticing that we over design power grids to make sure that they're largely behave. So to what extent are we, and to what extent, actually maybe a better question is, to what extent are we failing to do that because now we have solar and wind and all these messy things, or it's called the solar in my house, which really messes things up. So to what extent is this no longer going to be the case?
Yeah. So historically, yeah, we basically had like kind of more transmission capacity than we needed. We also had very centrally like placed power generation. So like some big power generators in some places, some load centers in some places, and the transmission system is designed around that so that everything works well. Kind of now it's we have kind of more distributed generation. So power generation is coming from more different places, like all of the rooftop solar panels everywhere. And then that is not necessarily being matched by building transmission capacity, like your lines, in places that are optimal for this. So sometimes lines now get congested that didn't get congested before, or you have like voltage issues locally that you didn't have before because your grid wasn't just like sort of built to handle kind of solar power in a particular place. Right. So that's actually what's driving us needing to solve these problems at greater scale and more proactively.
Right.
But then, yeah, it makes them harder. So stuff like this AC power flow solver convergence, there's like a whole body of research on just coming up with better AC power flow solvers that can deal with kind of more difficult scenarios. And the kind of nice thing about this implicit layers framework is if someone comes up with a better AC power flow solver that is solving the same equations, but is just doing it in a more robust way, I can actually embed that AC power flow solver in my neural network. Mm-hmm. And how I take derivatives doesn't change because we talked about the fact that like the process you solve the equations with doesn't affect the derivatives. You just need to know the equations and the solution. Okay. And so I think it actually provides a really nice way to kind of both ask questions about like, what are we willing to spend computational cost on? Like here we kind of online are okay to spend computational cost on feasibility, but we'd rather take offline all of the expense associated with optimality and kind of are okay with slightly suboptimal solutions in real time because they're faster than coming up with exact solutions. And then we do that by embedding numerical solvers. And now we can benefit from all of the research that's being done on the numerical solver side to kind of embed the latest and greatest into our neural network methods. So I think it's a very nice paradigm for hybridization, basically.
Got it. Cool. Thank you.
Yeah. Awesome. Cool. All right. So does this work at all? So to give an example on like a power grid test case. So 118 bus transmission test case is like, let's call it like a sort of medium size test case for a power grid. And we're going to compare 3 different methods. IP-opt, which is a sort of traditional optimization solver, just takes in the input, solves it, and solves online and gives you the output. A baseline neural network, where here it's trained using a penalty method. So it's just like, given the inputs, it's going to spit out an output, and the loss function is going to prioritize that it has like a good objective function and that it's not violating constraints. And then FSNet, which is our method that builds in these constraint enforcement layers into the neural network. So we're going to evaluate on 3 things: constraint satisfaction, objective value, and runtime. So when it comes to constraint satisfaction, what we end up seeing is that kind of our method, right, by design, we've built in a constraint satisfaction layer. So it's able to satisfy constraints. There aren't any violations of the constraints. Where sort of a neural network trained using a penalty method, where it like in principle is incentivizing constraint violations to go down, it's really not able to handle this very well at all. It has like big constraint violations. So then let's talk about the objective value. Like, is our neural network actually learning solutions that have good quality in some sense with respect to objective value? Remember, this is something for which we don't have a guarantee. This is what we're trying to learn to do well from data. And it turns out that our methods here are able to get like less than a 1% optimality gap compared to the standard nonlinear standard optimization solver, which in our case is good. Less than 1% is good. But then the benefit we get is okay, we have a constraint satisfying solution. Its optimality gap is not that bad. And what we end up finding is that we're able to do this such that online, when we actually run our neural network model, it's actually 10 times faster to run than kind of the standard optimization solver. So by basically doing a bunch of training offline, and basically then kind of using this learned model online, we're able to get a solution much faster than if we were using a standard optimization solver. Now, the solution is not as fast to obtain as sort of a naive neural network. You can see that there's sort of like a 40x, like a naive neural network is 40x faster to run than our constraint satisfying one. So there definitely is some computational cost compared to a naive neural network to embed this sort of constraint enforcement procedure in, but you still gain a lot compared to like the exact constraint enforcing and optimality procedure, the original optimization solver. So this is for like,
how fast does it need to be? You said 300 seconds. How often do you run these things?
Yeah, and so even though I sort of simplified at the beginning, like, oh, we have this problem, AC optimal power flow, we run it. They're actually different, like they're different problems that it's used for, each of which have different requirements. So sometimes you need it to run in basically like less than a minute. Sometimes you have longer, like you're like planning a future power grid and you want to understand what to do, but you're also trying to evaluate many, many more scenarios there. So like the amount of time it runs dictates how many scenarios you can run. So for operational timescales, you basically want, the ability to solve in like less than a minute. And for other timescales, there isn't like that hard constraint, but it's like the faster you get it, the more you can actually explore about what your future power grid will look like. Yeah. And so this is for like a 118 bus system, a smaller system. But what we're actually seeing is that as you actually scale this to bigger systems, the speed up gets even better. In some sense, like the scaling law for like the amount of time it takes for a constraint enforcing method to run is like kind of advantageous compared to the scaling, time scaling and the complexity scaling of like a standard optimization solver. So for example, for like a bigger system, like 1,000 bus system, which I would call like a big system, we're actually seeing like 300x speedups, more than the 10x speedup mentioned here. So the kind of fundamental thing here is that like the computational bottleneck in our pipeline is this sort of constraint solving procedure. But the constraint solving procedure, its computational complexity scales more gracefully than the overall optimization procedure. So that's what we kind of see reflected in our speedups. So those were some solutions on AC optimal power flow, but we also kind of, this is in some sense the method we developed is generally usable for parametric optimization problems writ large, where you have some class of optimization problems where their inputs are varying from one moment to the next. And so when we test our method on some synthetic problems, we actually find something surprising, which is that on some sets of synthetic problems, we're actually able to learn better solutions than the traditional solver, while also being faster and more feasible. So what's being shown here is 3 different classes of problems, kind of non-convex variants of a quadratic program, a quadratically constrained quadratic program, and a second-order cone program, where kind of the distribution of solutions found by the traditional solver are in pink, and the kind of distribution of solutions found by our kind of FSNet neural network method are in blue. And kind of, you know, for an easier problem, basically the solution distributions align. For harder problems, you see basically the solution distribution narrow for FSNet and actually be shifted left compared to the original solver. So what's happening here? What's happening? And these are all feasible solutions. So like all of these are solutions that are actually like satisfying the constraints. So what's happening here? What's happening is that for these optimization problems that are non-convex, there are multiple local minima that you could converge to. And a traditional optimization solver, its procedure for kind of figuring out which optimum it's going to converge to is data agnostic. It's just trying to figure out something that's good for any combination of inputs that could come in. Our neural network procedure, though, it's not data agnostic, it's data specific. We give it a particular distribution of training data and ask it to be very, very good at producing solutions for that distribution of training data. And what it turns out is that, like, for that particular distribution of training data, when you have knowledge about a specific sub-distribution, you can often learn to exploit additional structure in the problem that allows you to find better local minima. But then this means that the reason these solutions are working is because they're exploiting very problem-specific structure. Then when we're also, at the beginning, I mentioned this question of, can these models generalize? These two things stand in tension to each other a little bit, in the sense that we're finding better solutions because we're hyper-specializing to the problem structure. But if we want to generalize to other problems, do we actually lose that benefit? So I think that's a potentially like interesting notion of the fact that kind of what we're doing in amortized optimization is overfitting to problem-specific structure. So generalization can work, but also like in a kind of more limited sense. You sort of lose the benefit of fitting to specific structure if you also need a model that needs to be able to work in a general purpose way.
So question, I mean, this insight of tuning your optimizer to the origin of the problem space is very powerful. And you've pursued the neural gradient-based approach. There's also like the more evolutionary computation, run a LLM to generate code, in this case IP-opt variants that are only good in certain regions of the problem space. There are biased optimizers. To what extent is that useful? The not gradient-free search processes for these algorithms?
Yeah, it's a good question. I mean, I think if your goal is to like improve solution optimality, you could like do a lot to basically like even like add some constraints or add some additional information to your traditional optimization solver using any of these kinds of approaches to try to get it to come up with a better solution. But you're still kind of left with this issue that kind of online, you have to still like, when you actually are trying to solve the problem, you still like incur the full complexity of actually solving the problem online. So the neural network approach is allowing you to like amortize some of the computational cost by basically training ahead of time. And then when you actually need to solve the model, you like apply it cheaply. So yeah, so basically like this isn't meant to say that you can't tune a traditional solver to have better solutions. What it is saying is that the success of the neural network approaches is kind of the reason we're able to get good quality solutions is because we are intentionally fitting to a particular part of the input distribution. And we shouldn't kind of forget that as we then think about these notions of like, how do you generalize? Yeah.
Well, actually, I'm asking this, I think. So imagine I'm doing a Bayesian optimizer, gradient free. And if I want to tune it to find solutions faster in a given region of the problem space, I just like change the prior to say, this is what I think the problem is. So that's one way of biasing them. And it's not really established how to bias an IP op to find solutions only would be far more efficient in a given region of the space because it's biased. But with code generation, you kind of can do that. And this can be an alternative, or maybe horribly ineffective. I don't know, but it seems like it's a technology.
I guess what I'm saying is there's sort of two aspects, which is solution quality and solution speed at runtime. And I think what I'm saying is that the method you're proposing can be probably used to help improve solution quality by fitting to a particular part of the distribution space. But solution runtime is tougher. Like you can get better at solution runtime. Like you can also warm start your optimizer based on kind of solutions that are near where you want to get, right? But it's like fundamentally you still are incurring the cost of solving a constrained optimization problem live, as opposed to sort of pre-training and learning some of that complexity ahead of time, such that that complexity can be applied very quickly in real time. So you can improve the runtime of the solver, but I think there's a fundamental step change when you're like amortizing you're doing this like amortized optimization paradigm of basically training ahead of time and applying something very cheap live.
Right, because neural net would be incredibly cheaper for when it's applicable. Yeah.
Yeah, exactly.
Cool.
Yeah. Awesome. So I've kind of honed in on this amortized optimization setting when it comes to kind of embedding implicit layers into neural networks. And I just want to say that even though I've focused on that setting, this paradigm is more broadly applicable. For example, in an older paper, we looked at the setting of using reinforcement learning to learn energy efficient heating and cooling strategies for a building, where we wanted to make sure we respected equipment constraints and maintained thermal comfort. And here we basically just developed like a policy gradient, like reinforcement learning algorithm, where we have a neural network that's proposing actions, and then you project its outputs onto a set of feasible actions that you derive using domain-specific knowledge. That projection is an implicit layer, so you can kind of train this model end to end in the way you would a standard reinforcement learning model. And in the end, you basically end up getting like good energy efficiency outcomes, and you satisfy your constraints. So I'm not going to like dive into these results in as much detail, but basically I'm just trying to say this notion of like embedding some kind of like optimization or physical equation based constraint enforcer as a differentiable last layer in your neural network can be like a paradigm that applies across many different contexts, not just the optimal power flow context I talked about before. So in the last few minutes, I kind of honed in like very much on this first paradigm, right? Like this optimization in the loop machine learning approach, which is great because it gives you exact and provable guarantees about the feasibility and safety of your solution. And it's much faster than kind of doing this the standard optimization way. But it's still not extremely fast, right? There are some situations where you might want something that's like even faster, and you're willing to give up exact constraint satisfaction for that, but you still want constraints to be mostly satisfied. So another approach we've looked at is just basically learning approximate projections instead of kind of sticking exact projections into our neural network. And so we've asked questions like, can we train an autoencoder to basically, given the output of a neural network, to basically encode it into like a structured latent set, such that anything that falls into our structured latent set should decode to a feasible output. And anything that falls outside that structured latent set, we can kind of clip in latent space to the structured latent set and then decode to a feasible output. So basically like training an autoencoder such that a particular subspace of its latent set maps to feasible solutions, And then whenever we encode something that doesn't seem feasible, we can correct it very quickly in latent space. And we kind of end up finding, when we do this paradigm, we kind of test this on some small scale optimization problems where we're basically trying to minimize some objective while staying in a constraint set. And we look at constraint sets that are really weird, that like are disjoint or that are, star shaped or something like this. And we end up seeing that kind of using this autoencoder based approach, we can actually kind of come up with solutions that are empirically feasible. Like our autoencoder is able to learn to like map these solutions to feasible solutions while having a reasonable optimality gap and having a much lower solution times. Kind of this FSNet method in the second row is the method we previously showed. And this is now like, we are now kind of like a few times faster than FSNet in satisfying constraints in this area. So I realized that was a very, very quick tour through this sort of autoencoder based thing. I didn't really talk about the details at all. But all I want to basically say is in situations where you're actually okay, like you're willing to trade off guaranteed feasibility a little bit, in order to get like kind of another like 5 or 10x speed up in your model, then what you can do is basically learn like an approximate projector that is learning somehow to map between the output of your neural network and kind of a structured feasible set. And you can then apply that in your neural network. And we look at this both in kind of constrained optimization settings, and then we also look at this in like a reinforcement learning setting, where we find that like adding kind of this approximate projector onto a reinforcement learning model is able to kind of satisfy constraints of the reinforcement learning problem. So this is like a box pushing problem where you're trying to push a box from a starting point to a goal without hitting any obstacles. And we basically find that the amount that our model is like hitting obstacles is much less than kind of other safe reinforcement learning methods.
So is the trick then, okay, first of all, I'm a little confused how you evaluate constraints in latent space. And second, is the trick that because you project into a smaller space, you have some feasibility error, but this much smaller space means you can compute it way faster?
Yeah, so let me go into the details a little and then I can answer those questions. Yeah, all right. So our autoencoder is basically trained using 2 steps. The first is we're gonna just basically take like a data set of feasible points and then just like train an autoencoder to reconstruct points in that data set. So this is like sort of standard reconstruction error, standard training, just say like learn to represent this feasible set well. We then have a second phase, which is basically aimed at sort of structuring the latent space. And our goal is to kind of create like a structured convex subspace of the latent space such that solutions kind of solutions from the latent space decode to feasible solutions if and only if they lie in that part of the latent space. And so we end up then kind of doing a second stage of training on both feasible and infeasible points that tries to minimize some combination of reconstruction loss, a hinge loss that basically kind of prioritizes like infeasible points should really map, like points from outside the latent space should map to infeasible points, and points with inside the latent space should map to feasible points. We also actually have like a kind of like a discriminator or a critic that is basically like if you decode a particular point from the latent space, the subspace, if it isn't feasible, the critic will basically say, no, that's not good. And we also have like a geometric loss in there to ensure that like we have some uniform coverage of the feasible set. So basically there are kind of various loss terms that we're creating to basically say, if you're inside the latent, this latent subset, then you should decode to feasible, and we're going to penalize that if that's not the case. And if you're outside the latent subset, you should decode to infeasible, and we're going to penalize if that's not the case. So the reason we do this is the idea that our kind of actual constraint set in kind of non-latent space is potentially really like weird, non-convex, and therefore expensive to map onto. But the idea is somehow if we can represent this very weird set in latent space as a really nicely structured set, like a hypersphere, it's really quick to project onto a hypersphere. It's just like a very nicely structured set as compared to this output set, which is like very weirdly structured and expensive to project onto. So it's not just the dimension that is better, it's like the actual structure of the thing that we're projecting onto that makes it like much easier. Like you would have like a closed form projection, for example, onto a sphere.
Well, a lot of this hinges on having a neural net approximate your constraint system.
Exactly. And so like kind of this two-phase training process is basically meant to try to incentivize the neural network to do this well, to have this structured latent space. You also need good coverage of your training set in this process, or of your feasible set, sorry, within your training set in order for this to work. So this is entirely empirical, right? Like there's no like kind of guarantee at all that your output will actually map to something feasible. But I guess for us, it was still surprising that it like did anything, that it like worked at all. And notably that it like worked better than just a penalty method, which in principle is another way to tell your original neural network, please don't map to something infeasible. So yeah, it's basically like training like a specialized component to be like a good approximate projector, which is what we tried here. I think there's a lot to do to kind of make this paradigm, honestly, like a little less hacky and a little more scalable. But again, we were surprised that it worked at all.
Yeah, and the trick, if I may, it seems like you have these little regions where you just don't know where to push the bad solution to make it a good solution, and that's the main thing. Like when you have like this non-convex optimization, or how flip the optimizations, but to the extent that you can invert the weird space to turn it into a nice shape, you know exactly where to push it.
Exactly. That's exactly it. Yeah.
Okay.
And again, there's no free lunch, right? There's no guarantee here. If you could actually exactly always map from a nice shape to a non-nice shape and have that be exact, then you would like break something about P equals NP. Like, so this is all like empirical. This is all approximate. You're gonna have some places where you don't have feasibility. But nonetheless, maybe in some settings, you're okay with that trade-off where you're like mostly feasible, but way faster because of it.
Right. And one thing, this is applications in world modeling where you say stay mostly in laws of physics.
It could. Yeah, actually, it could. Yeah.
Interesting.
Yeah. So I realize we're running short on time, so I'm going to really kind of speed through the last part as well,
yes.
which is this safety encouraging. So another thing we do is like, okay, how else can we encourage safety? So we look at this paradigm in reinforcement learning, where basically like in reinforcement learning, when you're training an agent, you kind of have a way to sample kind of initial states for the episodes that your reinforcement learning agent will then like play out. And what we basically say is that if your agent encounters ends up in some episode where it does something unsafe, we want it to see that more. We want to like upsample places where it did unsafe behavior during training because we want it to learn to not do that. The idea that basically unsafety is like a rarer event in training, and yet that's exactly the thing we want to make sure it doesn't do, so it should see more of that during training. So basically all we do is we say, we're gonna, every time the agent does something bad, like it collides with an obstacle, we're gonna save the state, the starting state that caused that to happen, and then put that into some like unsafe, what we call a retrain area, some set of starting states where our agent didn't do something good. And then we're going to sample periodically for us our starting states from that in order to basically oversample places where we were unsafe to begin with, so we can learn to do better things in those situations. This also gives us good empirical behavior in the sense that we find that our methods trained this way end up improving safety. But the thing I want to highlight here is both in the previous paper with like the learned autoencoder and in this paper where it's just about upsampling a certain set of states during training, you don't know for certain that your states are, that your policy is safe. And in principle, before you deploy it into the real world, you would actually like some way to analyze is it safe or not. So what we actually do in the paper is we actually apply tools from reachability-based formal verification to basically verify the safety of the learned policies. And we're able to actually find and show, okay, like actually there are many places where kind of a non-safely trained policy would cause you to collide based on this reachability analysis, but ours doesn't. But then other places where we do find collisions as well. So I guess basically want to say like another paradigm for safety, like some of these paradigms for safety are during the training process, make sure you're doing something safe. We also shouldn't forget the paradigm of also like verifying after the fact, like are these models safe? And I think there's starting to be some really great ways to think about that. All right, so that is the very quick tour through safe machine learning for power systems, where we kind of went through different paradigms for either exactly enforcing constraints in the context of a machine learning model or approximately doing so. And some of the trade-offs there in terms of like computational speed, provable guarantees that we kind of navigate in that space. I started zooming back out by motivating that there are other things we also care about for machine learning and power systems. So not just safety, but things like robustness and generalization. And so I just want to kind of quickly mention two different benchmarks that our group has put out for machine learning and power systems to try to stress test some of these things. One of them is called PF Delta. It's a machine learning benchmark for learning the solution to these expensive power flow equations that I was mentioning throughout the talk. And we basically provide a kind of a benchmark and data set aiming to kind of allow people to ask questions like, how good is our ability to learn approximations to this problem? We also include some kind of, to your point, Greg, earlier about like, is the grid getting more complex? Are we having a more of a hard time now solving some of these problems? We actually put in some data samples that are explicitly like very hard to solve to try to then stress test how well can machine learning models deal with those. And then we also have tasks testing generalization across different power grid topologies and power grid structures. So this is available online. I would encourage people to check it out. And then on the reinforcement learning side, we have a benchmark out called RL to grid. This benchmark is focused on something called the topology optimization problem in power grids, where you're actually trying to reconfigure the lines and buses on the power grid in order to avoid congestion. And this is a huge and combinatorially sized problem. So I talked about this small-ish 118 bus system earlier. One substation, kind of one place in that particular grid has 65,000 configurations for that single substation. So this is a huge dimensional problem that doesn't actually have good systematic optimization solutions where reinforcement learning can potentially play a role. So I would definitely encourage folks to check out these benchmarks if you're interested in kind of playing with some additional problems in machine learning for power systems. And so with that, yeah, thank you so much. And yeah, if there are any questions and we still have some time, I'm happy to take them.
Oh yeah, this is fascinating. Yeah, and I guess if there's anything to get, it's just your opinions on the future of optimization, because this is kind of an ancient technology at this point. I mean, it is one of the first applications of computers, and now you're finding them in the like kind of expanding the space of what is acceptable, not necessarily optimal, not necessarily correct, using these neural methods. So where do you see the next set of advances coming from?
Yeah, so I mean, I think that we still haven't fully cracked this question of like how we deal with problems that are actually have no solution. So I talked about kind of this situation where some of these methods degrade gracefully if you have like an optimization problem and you have demand and there actually isn't a feasible setting of power generators. Like some of these methods degrade gracefully, but methods are not generally designed for this. Like when we have a neural network and we put in an input, we assume that some answer actually does exist. And so I think this question of like, how do we deal with these situations that are infeasible? How do we better suggest ways to repair the input such that there might exist a solution? Or how do we better communicate confidence in whether a solution exists or not? I think this is useful not just for optimization, but in general, in the sense that when we think about uncertainty quantification of outputs, I think when we talk about that, a lot of people are still in the frame of, oh, a solution exists. It's just whether the neural network is certain it found it or not. But the broader question of does a solution exist, which is not always the case, I think that also like needs to be bundled into this notion of uncertainty quantification. So I think that comes up very specifically in optimization, but also more broadly, and I think is an important place for these models to advance.
Got it. And maybe if I push one level farther, if I were to solve business economic kinds of use cases, now the design space is based on text and like complex time series, very multimodal. How would you incorporate? I'm just going to assume LLMs can capture kind of what people say about a problem, right? But how do you capture something that's squiggly?
That's a great question. And I think like this, the paradigm I talked about is definitely kind of geared towards places where we have like equations that we can characterize or
Right.
something like that. And I think sort of characterizing these things that are not like existing mathematical formulations we can write down, like I think that's I think it needs a completely different bucket of methods than this, basically. In some sense, like the whole reason machine learning exists is because we're trying to learn like rules in places where we actually don't have rules written ahead of time.
Right.
Now I'm saying we should apply machine learning in places where we do have rules written ahead of time, but the issue is the computational complexity of evaluating those rules. So I would say these are kind of two different settings, one where we know the rules, but they're just expensive, versus other places where we need to learn the rules. I think it's just a different bucket of techniques altogether.
Got it. Cool. Well, thank you very much. It was fascinating.
Thanks so much for the invite. And yeah, keep in touch.
Have a good rest of your day. Thanks.
You too. Bye.